go. And very soon.
Thanks very much. I retitled the presentation since someone else had written it. So I want to talk today about how depth cameras and the software that makes them useful can augment the augmented reality experience. And what I hope to cover today, and I know some of this will be old hat to some of you, is what are 3D cameras? What are the capabilities of the middleware options that support them? When and why would they be important to use or consider for augmented reality applications? Instead of or in addition to RGB inputs. I wanted to talk about the trends that we're seeing as a software company in the 3D camera and middleware sectors and what they might suggest for augmented reality, and then finally provide you with some of the better uses we've seen from various companies and research organizations using depth cameras for augmented reality. Real quick about Omek, we're not a hardware company, so we'll sit here and stand in proxy for the 3D camera industry. We are a software-only middleware company that makes software for body tracking and gesture recognition exclusively on 3D cameras. We're based in Israel. We work across all of the different depth cameras. So as we'll talk about later, the market for depth cameras is increasing and the number of providers is increasing, making the need for cross-platform tools more important, we think and we hope. We have two products, Omek Beckon, which is a full-body, mid- or long-range gesture recognition solution, and coming soon, a product called Omek Grasp, which is for close-range hand and finger tracking and gesture recognition coming to beta in Q4. I think most of you probably know what a 3D camera is, but in the event that a few don't, 3D cameras see the world in 3D. They provide depth maps, and the depth maps that most of them provide are fairly low in resolution. The actual working resolution of cameras like a PrimeSense camera, the Kinect camera, is on the order of 200 by 160. It's getting better, but it's pretty low, and so that's what they do. Some of them, as you know, also have RGB inputs. There's two major types of depth cameras. There's a few more technologies we're seeing on the horizon. The Kinect is based on what's called structured light technology. So it puts a pattern of infrared dots on the scene, puts that forth, and then analyzes through receiver how the pattern is distorted when it comes back into the receiver, and then essentially uses computation to determine the depth map. It's built from off-the-shelf components. There's a couple different ways to do this. PrimeSense uses one which is the basis for Kinect, uses one very complex pattern per frame. There's a company called Envision, which was acquired by Intel, which uses a simpler pattern and then projects it very quickly, and so looks at the differences across 10 different or 8 to 10 different patterns to composite the depth image for a single frame. All these things use off-the-shelf components, so they've been the fastest to market. Kinect was the first camera. PrimeSense was the one that was most ready, and they generate very good, high-quality data. As a middleware company, we're always looking at how good the different camera data is, and certainly structured light to date has produced the best results in terms of depth map. Time-of-flight cameras are based more on physics principles. They're not computational in nature. It's a dedicated sensor. It looks generally at the phase of the light that was emitted from our emitters on the camera, and looks at the phase when it comes back to the chip. That creates different issues such as aliasing, flying pixel effects. There's different types of noise, but ultimately we think they're likely to be lower in cost, more scalable in terms of resolution. The camera modules can be smaller because you don't have to have a separation between the emitter and the receiver. And the data quality is good. It's getting better. It is certainly not up to the level of the Kinect with any of the providers out there in the market yet. This is a picture of Omek Beckon. We're one of the middleware in the space. We support many different cameras. This is our viewer on 3.0. And we take these depth maps and we turn them into awareness of the humans. We identify the human forms in the scene, segment them out. We can identify well, 4 or 5, as many as really the cameras can see, provided you have enough computation and provided that the human forms are about 75% not occluded. So you can be a little covered but not completely covered. And then we track, we apply a skeletal framework onto the form, 21 joints in this case, and then track the positions and movements of those joints, which then can be coded as a specific gesture, positions or movements. So why is this important for augmented reality applications? I think we heard a lot from a previous speaker about the use of phones, and so when you're looking through a device or through a phone device, or if you have a phone as a controller, those types of interfaces are great. When you don't have a phone with you, or when you're looking at a screen as opposed to looking through a screen, depth cameras really offer superior performance in understanding the position of the individual in the scene and allowing you to apply the augmentations to that position. The data you get from depth cameras is a very high resolution. We have about 1%, about a 1% error is what most of them can deliver in terms of depth. So roughly 4 centimeters at a 4 meter distance, but very good imagery. The middleware, like ours or like that from Prime Sensor Microsoft, smooths out the form and so isolates some of that noise on a pixel level and allows you to get very tight maps on which you can overlay specific data, as we'll see in some of the examples. This allows greater visual accuracy of the augmented reality experience, and it allows for 3D accuracy. So we've seen a lot of the early sort of virtual fitting applications, which were based on just RGB. It has very much of a paper doll effect. You can't really turn your body. If you lean, things go very jinky. And things are very different when you start to use a depth camera, because you now have the positions and motions of all the joints in the scene, and you can create a much tighter experience. Microsoft recently filed a patent on the use of Kinect for positional audio, knowing where the head is, and allowing sounds to be placed contextually to where the viewer's ears are. Really does allow, depth cameras give you that information. So it allows for more than just the visual sense, which is where most of the experience has been focused, and allows for the incorporation of audio. Also would allow you to focus microphones for voice control, by way of example, which can be useful in a crowded space, identifying who is the major player. Depth cameras do have the advantage of doing the segmentation for you, so if you're concerned about computational load, they have that particular efficiency. And then finally, certainly one of the very important value propositions of depth cameras and gestures is that they allow for gesture-based interfaces, a way to control these experiences that you're viewing on screens while you're viewing them in ways that are natural and intuitive. People are very familiar with the Kinect, but the market is increasing vastly beyond that. There are cameras out from companies called PMD and Panasonic, Soft Kinetic, ASUS, PrimeSense, and Envision is coming out with a camera, and Samsung is coming out with a time-of-flight sensor, which will come out at the end of this year, and we'll see camera modules on that. And there are other providers as well. Since time-of-flight is difficult to do, I think that represents pretty much the known universe of time-of-flight developers. Infineon is also building one based on PMD designs, but we will see also other structured light cameras coming out from different companies, because it is something that can be done with a good software team. Why is this important? Lower costs, differentiated capabilities. The range of time-of-flight cameras is longer. They operate in different lighting conditions and through glass. And it also offers the possibility of having multiple cameras directed on a scene and allowing you to apply augmented reality to a large number of people at the same time. Resolutions are going up. We're seeing the first production QVGA units now. The VGA cameras are about a year away, we think. And we're now seeing frame rates in the 60 to 90 frame per second range, which allows for a much better and tighter and smoother experience. I think one of the criticisms of the Kinect has been the latency of the experience. And so as frame rates go up, it gets smoother. Other things will help with that. It just allows for better reality augmentation. Prices are dropping. Performance and pixel performance is increasing. We're now starting to see close-range cameras on the market. This is an example of a PMD close-range camera. So these are designed for laptops and tablets and automotive applications. They have a range of under 1 meter, 50 centimeters is really the sweet spot, so it's designed for hand and finger gestures. Other vendors will ship this year, so it's a whole new market for augmented reality. No longer have to stand that far away. The quality of the tools continues to improve. You're starting to see embedded versions and also the middleware sitting closer into the camera module, which will also reduce the latency, which will benefit AR applications. And then the close-range middleware is on its way. We're working on it. Omek Grasp. Other people probably are as well. And that'll usher in, we think, an exciting new era for AR. I pulled a few examples of compelling applications using depth, so let me show you what some of the other people have done, if we can. So this particular application shows it's a MRI and CT scan data that's applied over a human body. It shows the tightness that you can get, but also how you can lean forward and backward and maintain the integrity of the skeletal information relative to the camera, which would be difficult with 2D approaches. Cisco has recently released the StyleMe system. See if we can get that one running.
As Will touches a region on the map augments data on top of the map. You can see that South America is highlighted, and the sales performance...
So in this example, this is a database company using an application to show the power of their database and augmented reality of 3D visualization using wearable 3D glasses and a Kinect camera.
Here's a holographic video call that we can see through the mirror. So there's just
we turn the volume up.
We can imagine this could be a live image of someone that I'd be talking to. You'll notice that it will actually switch from one hand to the next, so I can hold this little version of myself. So it's kind of a fun Here's a holographic video call that we can see through the mirror. So there's just a video of me. We can imagine this could be a live image of someone that I'd be talking to. You'll notice that it will actually switch from one hand to the next, so I can hold this little version of myself. So it's kind of a fun idea of communications in the future. So as another example of what we can do to combine the phone with the holoflector is we have this basically this wooden paddle that we're rendering. And so one nice thing about using the phone is that we get the nice orientation data from the phone, and we're also using the position data from Kinect. And then finally, we can demonstrate interacting, say, with a fluid simulation. The Kinect data is now colliding with the various particles on the display for this kind of interesting experience.
We'll try that first one again.
Augmented reality is the melding of the real world with computer-generated imagery. It seems the perfect medium to investigate magic and ask why in a technological age we continue to have this magical sense of wonder. Magic is deception, but it is a deception we enjoy. To enjoy being deceived, an audience must first suspend its disbelief. It was the poet Samuel Taylor Coleridge who first suggested this receptive state of mind.
I try to convey a semblance of truth in my writing, to produce for these shadows of the imagination a willing suspension of disbelief that, for a moment, constitutes poetic faith.
So to wrap it all up, let me conclude by saying the availability and quality of the depth cameras and the middleware that makes them useful continues to expand, and the costs are going down. The applications for AR in terms of enhanced accuracy and natural gesture control are significant and only beginning to be explored, and opportunities exist for leading innovators to combine AR and depth sensing technology to redefine interactive experiences. Thank you for your time. If you're interested in using Beacon, please come to our website and download it. Version 3.0 is coming out in 1 month. And if you're interested in the close range Omek Grasp software, please send us an email at info@Omek Interactive. We're taking applications for alpha now, and of course, we'll have a wide beta in November. Thank you very much.
So, questions for John? Looks like we have a couple of, if you don't mind again, just coming up to the microphone.
Jonathan, Greg Panos. Question about the, what happens when we get to a point where people have these two variants of depth tracking camera systems, and there's lots of them in an area, and each one is projecting either a structured light reference pattern from its point of view, or trying to do other measurements with other infrared light that's being emitted. Will they interfere? I mean, do you see, are you making any accommodations in your middleware for multiple users in multiple spaces using the same technologies that use the same kind of referencing?
So we haven't done that, but some of the, it's a good point. I mean, I think we're a little ways away from the time when we have wearable depth cameras, and the main focus is on the camera looking out at the scene versus people wearing depth cameras. But certainly Panasonic, at the very least, and a few other vendors offer multiple frequency options. Right now they have 3, but there's no reason that to avoid that case. You could allow people to have individual frequencies, but there will be interference if things are too close. It would be one of the challenges with this.
So there might be some sort of collaborative frequency assignment scenario when a bunch of people join a space?
I think you'd have to. I don't think there's an infinite range. So you'd have to bet that there were sort of like garage door openers that you could be. There could be enough that you would not accidentally open the other guy's.
So if there's 100 available and there's 50 people, then they immediately enumerate at 0 every 5 minutes or something like that.
I'm not sure of the particular scheme, but that would be the way to solve that. But you've identified one of the issues. So again, right now for location-based stuff, they have up to 3 different frequencies that they can work at, and that avoids issues with crosstalk.
Great, thanks.
Thank you, Greg.
I'm wondering, the Omek Grasp product, are there any restrictions on the hand pose, or can you basically have your hands in any position or pose?
So it will. You can have it in any position like this. It will. It can break down when you have certain very tight. We recognize a fist. If you have certain very tight occlusions in the first versions, those are not able to be resolved. That's certainly something that we believe that we can get a better handle on over time. But the benefit of the close range stuff is much more finesse. You can make very finessed movements. This can be a click if you want that to be a click, as opposed to having to do the sort of large swipes that have been required by RGB approaches.
Okay, thanks.
I have a rather, I guess, elementary question. When it comes to the gesture recognition, a lot with Kinect that I hear from people who just play with it is they say that it's very unresponsive, or you have to do these very exaggerated gestures. Is that the technology, or is that more of the application in the interface?
I think there's a couple reasons behind that. So one is the frame rate of the Kinect camera is about 30 frames per second, so that introduces latency. They've done their middleware computation on the device itself as opposed to on the camera module. So there's time for the depth data to travel uncompressed and be processed. So that's something that can be reduced also. So we think that right now the estimates vary, but it's roughly 125 millisecond latency, definitely noticeable. As resolutions go up, as frame rates go up, and as the processing for gesture recognition, the gesture part, not just the depth part, goes before sort of in the camera, then we think we can reduce that to around 50 milliseconds, which should be a much more savory experience. Thank you very much.
Is that 1.5 or 5.0? I didn't hear.
5.0. 5.0.